Now this general theorem for integration and differentiation of power series will be also very useful to find power series representation for more functions. Consider for instance this function, f of x is natural log of 5 minus x. Well, it's the type of techniques we discussed, which essentially comes down to representing a function as some variant of a sum of a geometric series. There's not a lot we can do directly on natural log of 5 minus x. However, if we look at its derivative, when I differentiate natural log of 5 minus x, I get 1 over 5 minus x multiplied by the derivative of 5 minus x, which is negative 1. That's 1 over x minus 5. And you might remember that this is one of the examples we treated when we first discussed power series representation of functions. This is 1 over a linear factor, and we know what to do with that. We look at the constant at the bottom, negative 5, and we factor it out to make it a 1. So in other words, we factor out negative 1/5, and that means that when I factor it out of negative 5, I get 1. Out of x, I get negative x over 5. So we get negative 1/5 multiplied by 1 over 1 minus a common ratio of x over 5. So that's the sum of a power series of first term 1, common ratio x over 5. So I get negative 1/5 of the power series x over 5 to the n, which is x to the n over 5 to the n. And that's valid for absolute value of x over 5 less than 1, which I can write absolute value of x less than 5. Now the 1/5 in front, I can bring it in and write it as x to the n over 5 to the n plus 1. But in any case, what's important here is that I have a power series representation for f prime. And therefore, on the same interval from negative 5 to 5, I can integrate term by term the power series representation for f prime, and I get a power series representation for antiderivatives of f prime, and f is one of them. So for some constant c, f is an antiderivative of f prime, which is negative the integral of my series, which is the sum of 1 over 5 to the n plus 1 multiplied by x to the n plus 1 over n plus 1 up to some constant. And now all we need to do to get our power series representation is to find the constant c. And to find the constant c, we're just going to evaluate the function f in two ways. We know that we have f of x under the form ln of 5 minus x, so in particular f of 0 is ln of 5. On the other hand, we have f as represented as the sum of these series up to a constant. So when I plug x equals 0 in my series, you see that all the terms in the series have a positive power of x, because even for n equals 0, I get x to the 1. So when I plug x equals 0, I get 0 for each term. And therefore, what remains is just c. I get 0 plus c, just c. So the constant c has to be natural log of 5, which gives me my power series representation for f of x as negative series from 0 to infinity of x to the n plus 1 divided by 5 to the n plus 1 times n plus 1 plus ln of 5, and that is valid on the open interval from negative 5 to 5. Now to do one more example before we turn to another video, we want to find a power series representation for the function 1 over 1 plus x squared. Doesn't quite fit the pattern that we have explored to obtain power series representation using the sum of geometric series. However, you can notice that the integral of the function, it's an antiderivative of 1 over 1 plus x squared, so that's 1 plus x to the negative 2, and antiderivative is 1 plus x to the negative 1 over negative 1, in other words, negative 1 over 1 plus x. And for these kind of things, I know what to do. I can write 1 over 1 plus x as 1 over 1 minus negative x, and this way I obtain the sum of the geometric series of first term 1 and common ratio negative x. So I get the sum from 0 to infinity of negative x to the n, which I can write negative 1 to the n x to the n, and that's for the common ratio negative x less than 1 in absolute value, which is the same condition as asking the absolute value of x to be less than 1. So that's for an antiderivative of f. We have this type of power series representation. I should have written it up to a constant, but it doesn't really matter for what we want to do, because now f is just a derivative of this antiderivative, and therefore to obtain a power series representation for f, I can just differentiate term by term the power series representation that I have obtained for integral of f. And I obtain the the opposite of the sum from 1 to infinity of -1 to the n and x to the n minus 1 for the same open interval from -1 to 1. It's not very important, but we can rewrite that. If we want to start at 0, if you think of how it starts when n equals 1, x to the n minus 1 is x to the 0, so you get the constant term. So we could rewrite that in terms of a new index k, which is n minus 1. And in that case, when n is 1, k is 0, so we start the series with k equal to 0. When n goes to infinity, so does k, of course. N is really k plus 1, so -1 to the n is -1 to the k plus 1. N is k plus 1, and n minus 1 is k. So we rewrite this series in that form in terms of the index k. The negative sign that is in front of the sum, I can pull it in, and then I get -1 to the k plus 2, which is really the same as -1 to the k. So I can think of that as the sum from 0 to infinity of -1 to the k, k plus 1, x to the k. And so if I want to rewrite it in terms of n, I can. It's just changing the name of the index. And this is true for the open interval -1 to 1. In the next video, we are going to look at more applications of this type of idea.